Hello and welcome to Deep Learning. Today we'll talk about the attention mechanism. So recently transformers have been quite impactful in deep learning, and they're fundamentally based on this attention mechanism. It's a pooling operation that we will explain today. So let's dive right in. Before we start, let's start with a motivating example. Say we have a database that consists of keys and values. For example, a database of first and last name pairs. So we may have Schumacher as last name, Anna as a first name, Schneider, Michael, and so on and so forth. And in all of these cases, the last name would be our key and the first name would be our value. So we have keys and values. The keys, the last name, the values, the first names. And now we would launch a query queue on this database. For example, if we ask for Schultz, then we would expect to get a return value of Lisa if the query is exact. So we would look for the key Schultz and then find the tuple Schultz Lisa and return the value. So that's what we would do in a standard database. Now, if this entry Schultz Lisa was not in the database, well then the return would be empty. We would get no answer. Now for the case where this example Schultz Lisa is not in the database, and if we made the query, for example, approximate, so if we allowed for differences between our query and the key, then we might, for example, get for the query Schultz, Schuler, which has quite a low edit distance to Schultz. So we might retrieve the value Tim. So we realize that queries operate on key value pairs regardless of the database size. So the same query could be applied to this database, it could be applied to a larger database. The query stays the same, but the response might change. And depending on the contents of the database, we might get different answers. We also see that queries tend to be relatively simple, but that the complexity is sort of embedded in the database or in the state space. And we might think of different ways these queries could be executed, for example, in exact fashion, an approximate match, or we can also think about doing a top K query that gives us the K most similar responses back. So why do we talk about database samples and queries here? Well, the attention mechanism translates this concept of having key value pairs and performing queries on these key value pairs to deep learning. So the central operation in attention is called attention pooling. So it's a pooling operation, similar to average pooling or max pooling before. So how does this apply here? Well, say we have these key value pairs, little m of these, where ki, vi is a tuple that corresponds to the ith key value pair. And we want to perform a query queue on these key value pairs. Then attention is a function that takes this query and applies it to this database D. And it's defined as the following. It takes the sum from I equals 1 through m and goes over all of those tuples, takes the ith key, and evaluates a function alpha on the query and the key. So it basically performs some form of query to the keys, and this creates some value alpha and applies it then to the values. And as we see, the values are multiplied by the result of this function alpha. So we're basically building a weighted sum over all the values based on this function alpha. And what is alpha? Well, it's a scalar function that is what we call attention weights. So our query applied to a key in the database produces this alpha attention weight. We can think of this as basically, if alpha, this attention weight, is large, then this attention mechanism or attention pooling pays a lot of attention to this particular key value pair. So in this weighted sum, the corresponding value will receive a large weight. So because building this weighted sum, the keys that receive a large amount of attention will receive large attention weights, and the resulting weighted sum thus will weigh up the corresponding values. So let's visualize this again. We apply our query Q to our database that corresponds of these M keys and values. So we have these tuples in order to take each key and evaluate this function alpha over all of these keys. This gives us our M different attention weights. And then based on these attention weights, we create an output that is the sum over all of those attention weights. As the output. And because we are applying this to all the values and reducing all the values to a single weighted average value, this is actually a pooling operation. So you can think of, if all those alphas were the same, then this would just correspond to standard average pooling. If we would do a top 1 query, this would basically be some form of max pooling. But this is sort of a generalization of other pooling operations because it's some form of weighted sum over all of these values. Typically, these attention weights, they are chosen, so these functions that produce these attention weights are chosen to be non-negative, no matter what the query or the key would be. And if they are non-negative, then this weighted sum is basically contained in what we call the convex cone spanned by the values I. What is a convex cone? Well, if you view our vectors vi as, this is v1, v2, v3, as vectors, then if we multiply each of those vectors by some weights, say this is alpha times v1, this is alpha 2 times v2, this is alpha 3 times v3, and we build the weighted average, then we will get a weighted average that somehow lies in a coordinate system that is spanned up by these 3, but as all the alphas are non-negative, it's basically a coordinate system that starts it here. So we won't get ever a weighted sum that is outside here, but we always basically operate in this sort of cone, right? So it's basically some space that goes, that gets larger and larger. So it looks a little bit like an ice cream cone. So if you have many of these, it gets rounder and rounder also. And that's why we call this a convex cone. So think of this as basically having here its origin and then the cone coming out. And yeah, you could put some ice cream, for example, into this cone. Yeah. Now, if we additionally make all the alphas sum to 1, so if for the sum of I, alpha q ki is 1, then the response still lies obviously in the convex cone, but it's actually, we call then the resulting sum a convex combination. And if exactly one of those weights would be 1 and all the others were 0, that's still a convex combination, but we basically build a convex combination by allowing the weighted sum only to pick a single one of these vectors. Then we are basically doing something that is very similar to max pooling, where you get a single value back. Another special case would be if one where all the weights are equal, so you no matter what the query and the key are, you always get 1 divided by m back, then you would just build the normal average. So we see that there are many special cases depending on how we define these attention weights or the function alpha that gives us the attention weights. Typically, they are non-negative, or often we would have this additional constraints that all the weights sum to 1, with all of them being larger or equal to 0. If we want all those attention weights to sum up to 1, we can achieve this by normalizing them. So for example, we can take any function alpha that we define on the queries and the keys, and by dividing through the sum of all those alphas, so basically alpha applied to all the keys, we achieve a new alpha that is normalized, that sums to 1. And if they're all then also larger or equal to 0, this would result in a convex combination. How can we make them all non-negative? Yeah, well, for example, by exponentiating each of those. So the exponential function can not be negative. So it's a non-negative function. So no matter what the value range of this alpha values is, exp of alpha will be non-negative. The reason is that e is a positive number, and if we take, say, a negative value 0.3, say, that would mean that we're basically computing something 1 divided by e to the power of 0.3, which is again a positive number. And by combining this exponentiation and this normalization, so here we exponentiate, here we normalize, we actually get something that looks very much like a softmax. And so applying softmax to any function a, we achieve that our attention pooling, so the softmax attention function, is always a convex combination of the values associated to the keys. The benefits of using the softmax function is that it's implemented in all the deep learning frameworks, because we're also using it for classification in the output layer. It's of course differentiable, and the gradient never vanishes. Now, this is not the only possible attention function or the only way to construct an attention function. So there are alternatives. We can even use non-differentiable functions. Now the problem is that non-differentiable functions are not so easy to train, so we have to think about other mechanisms to train, but this could, for example, be done using reinforcement learning, which is outside the scope of this particular course. Now, the benefits of attention mechanism, especially if all of those weights are non-negative and sum to 1, it's actually quite intuitive and can be understood quite well, because we're basically saying, okay, well, we can spread our attention over all of these data sets, and we're sort of assigning weights that have to sum up to 1 to these, our attention, or total attention. And we can basically interpret as large weights as the ones that basically being the values that the feature, that the model wants to attend most and puts the most attention to. Now, while this is interpretable and we get a good intuition, it's still just an intuition. Yeah? So keep that in mind. So let's summarize this part. Attention is a way that allows us to aggregate data from many key value pairs. It is a differentiable way by which neural networks can select different elements from a set of key value pairs to construct a weighted sum over these representations. Now, while we have now explained how attention works, the question is, how do we get these queries, keys, and values in machine learning? Well, in the next lecture, we will see an example where this mechanism is used to build regression models, and that's a so-called Nadaraya-Watson estimator, kernel density estimator for regression. In this case, the query corresponds to a location where we want to perform this regression operations, where we want to predict the value, and the values are the output of the regression value themselves. So you can think of this similar to basically performing a query here. And here you, at this query, you have many different values, and you're sort of using the query to all of those keys to build a weighted average over all of these outputs, and that is your predicted function. But let's talk about this more in the next lecture. Now, this is one way to do it, but there are many ways to do this in deep learning, and we will see many ways of these, because in principle, any of the queries, keys, and values are differentiable, and thus they can even be learned from data. And that is what's done in deep learning, and that's what will lead us to the transformer architecture. So I say goodbye for today and see you next time.